Okay, welcome back to another exciting Java class. This is recording in high def, 1280 by 720. I don't know what that's going to do to the size of the file when I go to upload it, but I imagine it will make it larger, because normally I'm at 800 by 600. But I thought I'd try something different for a change. I've found a solution to the homework for equalization using the FFT, and it was written by Rich. And what I did was I created a poorly packaged class in the address book package, and since it doesn't belong there, I'll move it to oh, I guess I can't. I'll have to move it later. Let's see what I can do to make this stuff that you wrote, Rich, work. Paste. Oh, so this is what happens when you submit stuff and you don't package it right. Here, we'll just take this part out, and now all the errors went away except for one, and it's this one that says it's public. And what we'll do is we'll give it the name RK. And now there's probably another problem because there's another RK down in here. You can delete that. I still can't get your thing to compile because this has to be called RK. This is what I get for renaming everything. What's this? Oh, RK. Probably should have been a little bit more organized about it than that. But life in the big city, too bad. Now, what do I do? Just run it? And this works and everything? We'll see if it works. Oh, wow. There's like an interface here and everything. So, let's see. I see sine waves, that's good. Now I can do an open. Now I gotta find an AU file, isn't that right? Okay, so let's see. Let's find an AU file, and what do you recommend? Space music? Okay, let's try that. So here's some space music, and now I should be able to do something to do this, right? What shall we do? Take the FFT? First, drag the sliders. Like that, maybe? Uh-oh, wait, stuff is coming out on the bottom here. Oh, wow, look at that. Numbers. There's numbers coming out. And more numbers. Okay, so I did stuff. Now what? Play it or take the FFT? Just play it. Oh. Okay. Hopefully? It sounds the same. Let's crank this part and see what happens when we play it. Ah. Now let's play it again. Now, tell us about your algorithm, Rich.
So, when I did the FFT, it kind of destroyed it.
You did what now?
Like, when you did the FFT once and then did the inverse after scaling, it really messed up the algorithm.
Messed it up.
Yeah. Like, you lost a lot of information. So, what I tried instead was I did scaling on the data directly. So, I found the maximum frequencies.
Mm-hmm.
Broke up the data in the groups of 4. And then I took this sliders and scaled the data that was in the ULC. So the closer to the center ones would be the low frequencies, and the further away from the center were the higher frequencies. And that seems to have the correct effect.
Whoa.
that adjusts everything that's on the...
Are we seeing this in the frequency domain? Because I took an FFT.
Yeah, that would be doing it on the array of the FFT data.
So, if I play this now, it should come out as silent, right?
Should, yeah.
That's good. Now if I go up in here, look what's going on. It's alternating.
That should be all the highest.
Why is it alternating like that?
It does the top and the bottom at the same time.
That sounded good. Not.
Oh, I didn't do the FFT when I did it.
Oh.
I did it on the original data directly.
So what's all this looking at? Oh, I'm trying to do your algorithm on the FFT data.
Yeah.
Oh, that's bad. That won't work.
I did it on the original.
I have to have the original data. Oh, because we're doing an FFT on the FFT data, and so we don't get a chance to see what's going on. Okay, let's try Techno Machine, because I can't really see what you're doing in the frequency domain then. Alright, so now if I go and I do this, alright, so let's add some lows and alrighty then. Did everybody else get sort of similar results? You did it a different way. How did you do it?
I computed the FFT of the data, then I got the real and imaginary parts of the data, then I multiplied them by the value of the sliders, which I made in between 0 and 100, and divide that by 100, so it was a percentage of between 0 and 1. Scaled all the real and imaginary parts, I scaled them, and then I put them back in the compute backward FFT, and then played it, and then, yeah, so there.
Let's go to the next one here and see what's next. So the next one is Albert. Let's see what Albert did. I got a big zip file here. Let's see. Albert says the equalizer is found within the sound equalizer. Taking the form of what was done in class, the grunt work was to take the getEqualizedData function. Within this function, the FFT data was already computed from the FFT object. Using this, FFT object normalize is used to normalize the FFT data. From here, a new function called newFilter is used to parse through the normalized FFT data and supply the appropriate amplitude to the correct chunk. So is this kind of what you did? You worked in the frequency domain.
Yes.
And then a new FFT object is initialized using equalized data. From here, the non-normalized PSD is returned. When started, the program needs to be selected in a WAV file. Oh, a WAV file! A WAV file! Ooh, fancy! A WAV file. So that's good. Since Albert's not here, I will defer that inspection till later. And let's go to Brian's code. What do we got here, Brian? Equalizer.java. Download. Okay. Show in folder. Okay. Open with IntelliJ. Oh, really? Ah! Okay, let's not do that. Open with... What can I open this with? Notepad. WordPad. Yeah, WordPad. So now, what is this called? Equalizer. That's a good name for it. Select all, copy, close, minimize, and now what we'll do is we'll go into the sound, the sound package, and we'll make a new class, Java class. Let's call it equalizer, E-Q-U-A-L-I-Z-E-R. Lots of fun. It already exists. Okay, equalizer 2. I know. Let's call it BA. Right, we know whose it is. And then we'll just kind of paste it in, and we'll go to the top. And here's where it says BA, so we'll just delete that. And then, oh, he doesn't like this. Let's call it equalizer 2.
BA.
Equalizer BA.
No, I mean you already have it BA.java.
Oh, let's call it BA. Now what? He's unhappy. Oh, he doesn't know how to do a run for slider panel data. What's up with that? Did I like forget to include some kind of class here?
That comes from
Yeah, it comes from the run for slider panel data. Did you make up your own run for slider panel data?
no.
There's something at the top.
So
Very top.
I got what now?
There's an error at the very top. Maybe missing an open or something.
Where's that error on the top? I beg your pardon?
No, I know that thing at the red square at the top.
The red square at the top. This one.
Above where he's
He's telling me he doesn't know about run for slider panel data.
I think Rich is referring to the top right red square above the yellow square.
This one?
Yeah.
That's the same thing. How'd you do that, Rich? Did you use the run for slider panel data also?
Yeah, for that I used your code that we got.
And where's that at? I'm not seeing it. Run for. So it's called run for slider panel, not data slider.
Those are two different things.
They are different. Did you want this?
No.
No. Where did you get that? I never heard of this. Is this something else?
Because I called it private.
Really?
Not even paying off.
I got confused. I don't know where that comes from. I can't get your code to work. I don't know what the heck's going on
I
here.
have it from your code.
You do?
Yeah. Package GUI.run.
Okay. Package GUI dot run for slider panel.
I have public class run for slider panel data.
Where'd you get that?
GUI.run for slider panel data.
I don't have that. You want me to do a search for it? Find in path. Find in path. Paste. Whole project. Find. That's you. That's your data.
I swear I didn't make this up. But
Yeah, no, it sounds like something I would do. Maybe there's a small synchronicity issue where my code got updated or something got changed, because this looks like an array of spinner number models.
yeah, that's just to set the spin.
Yeah, especially where the quads are coming back. So
I brought that in to change the spinner number model. You see, I went from starting at 100 with min 0, max 100, step size 1.
yeah, I see that.
Yeah. That's why I used that.
Well, I'm having a little difficulty getting the code to run right now, and I don't want to take too much class time with it, so maybe we can do that during the break. Who else wants to have a go at it? Anybody? Nobody? Mike? No? Arodi? You're still having issues? Okay. So what we'll do here, not to sort of get hung up on it, because nothing will compile as long as there's one error somewhere. I'm going to take this lovely program which you've written, which is really very nice, and I'm going to delete it. This really wonderful program, just so I can get things to work again. I mean, it's not like I didn't, I wanted to do it. I had to do it. The compiler made me do it. Uh-oh. What's going on here? Oh, it's got the BA in there. I want the RK. Yeah, this is. Well, it tried to. I am. You mean this won't work now? It's working. So there. Okay, so well, that was all very educational. Did anybody take the approach of doing a short-time Fourier transform or a short-time discrete Fourier transform in order to do the equalization? Because I think that's the key to doing real-time equalization. Real-time equalization, in my view, is equalization that runs in the amount of time it takes for the data to be sampled. So when somebody says, what's real-time signal processing? It is processing at a rate which is as fast or faster than the data appears. As fast or faster than the data appears means real-time is known if you know your application's specification well. So you can't, the answer is, it's a trick question, the problem's ill-posed. It's real-time if the data is coming in a time which is slow enough so that you have time to process it. That's real-time. So when someone asks you, is your data processing real-time? The answer is, it depends. It depends on how fast the data is coming in. Right? So if you told me, well, we're sampling at 8 kilohertz and we've got this giant, core, dual-core i7 Intel processor, yes, it's real-time. But if the data is coming in and it's 16-bit stereo and all I have is an 8-bit toaster controller Arduino piece of duty, then the answer is no, it's not real-time. So it kind of depends on something like the throughput of your processor, how much data is coming in, how much memory you've got. These kinds of issues are kind of important. If you told me I got a real-time equalizer and it has 2 bands, I'd say, okay, no big deal. But if you said I got a real-time equalizer and it has 2048 bands, I'd say, okay, sounds like you must have an FFT running in there somewhere or a fancy signal processing chip. Because otherwise what's going to happen is it'll be too slow. So equalization is one of those things that, if you think about it, you really want to be in the frequency domain. That really does help you. But it's not necessarily the case that you have to be doing an FFT. You could be doing a DFT. Depends on how many samples you want to do at one time. So real-time's interesting. Interesting question. The other thing we examined was the crossover. At what point is an FFT required in order to go faster than a DFT? And the answer to that question is, it depends. Again, it depends on the processor, it depends on how much data you're trying to chunk, and it also, I think, depends on something or other about how much memory you've got. because a lot of times when you look at the FFT, it's very memory intensive, right? You've got these real samples coming in, you've got to make a copy of the whole thing and make a complex array. Now you've got two things, and one was integer when it came in, and now it's floating point internally, plus you got a complex array that's floating point, so now you've taken integer input and two floating points, they're both complex, both in the same size. Then you've got to do the inverse in-place transforms and do all the twiddle swapping if you're going to do FFTs, and it becomes very memory intensive. It's very good if the CPU has a large cache, because then you can make things run really fast. But if the CPU is running on slower memory, then things could get a little bit slow and maybe it won't be fast enough. Got another problem for you. I mean, if you're looking at an Arduino and you're thinking, geez, you know, maybe I only have 1K of RAM on chip, that's really not enough to do a full-fledged multi-sample FFT or DFT. So doing gradual short-time FFTs might make sense, or gradual short-time DFTs, just because you don't have enough space. So lots of interesting problems in signal processing that will make practical signal processing something that requires very pragmatic considerations. So that's my sort of speech on signal processing in real time. The other thing we examined was correlation. And I wanted to revisit correlation and talk to you a little bit about correlation again, only this time with a difference. And the difference is, the correlation I want to talk to you about is called autocorrelation. So let's do a little review about what correlation is. And in the one-dimensional signal processing world, correlation is one-dimensional signal processing between two vectors, where the vectors are just signals coming in sequence. And you can do this in a streaming fashion with a short-time correlation. So if you remember the dot product, everybody sort of remember the dot product? A dot product is when you take two arrays and you multiply them together, and then you do, after the piecewise multiplication, you add it all up. So if you were to write this out, it's AX times BX plus AY times BY plus AZ plus BZ. That's a dot product. Got that? If you just had to do this with AX times BX plus AY times BY, where those are two vectors, then what you're really doing is you're multiplying by the magnitude of the vectors, magnitude of AX times the magnitude of BY, and then you multiply that by the cosine of the angle between them. That's how you define the dot product in the two-dimensional Cartesian coordinate plane. You guys probably remember that junk. If you wanted to do it in 3D, you could do it in 3D with the three components X, Y, and Z. But here what we're doing is we're going to take a completely linear algebraic approach to the dot product. Right? Just piecewise multiply, then do a big addition. And that's it. Now think about the correlation. The correlation between two vectors is actually a sliding window dot product. So what this is doing is it's a piecewise multiplication of one vector times another vector with some offset, and you add it together, and then you go and you take that second vector, you see where the j is, and you change j a little bit, and then that causes g to start to slide. So you slide g by over by one increment, and then you do a dot product again, then you slide g over again, and you do another dot product, and you slide g over again, and you do another dot product. In fact, you got to slide g over as many times as there are increments in f. So that means you're doing a whole bunch of dot products, right? A ton of dot products, one for every sample. And so that's kind of slow, right? That's an order n squared operation. So now all of a sudden, you know, it's a sliding window dot product with a difference. And the difference is that little star next to the f. What's that star mean? You see where it says f sub j star? What's the star for? Yeah, it's a complex conjugate. How do you make a complex conjugate? Arodi, what are you doing over there? You're not playing Netscape, are you? No? Okay, so how do you make a complex conjugate, Arodi? You don't know? Okay, it's important that there be some learning in this classroom. Mike will tell us what a complex conjugate is. Oh, crap. Rich will tell us what a complex conjugate is. Multiply by -1. Okay.
In the form of A plus BI.
Yeah, if x plus IY is a complex number, then the complex conjugate can be stated as what, Kevin? It's x minus IY. Thank you. Yes. So the part, you know, Rich was kind of right. You multiply by -1, but only the imaginary part. So you're really multiplying by minus I. Remind me not to flash equations up in here before I start interrogating you about what they mean. So now if you look at the left-hand side, you notice that star is different than the star on the right-hand side. Arodi, how come there's a 5-point star on the left-hand side instead of the asterisk like we see on the right-hand side? It's a different operation. That's correct, Arodi. And what operation is it? Oh, crap. It's what now? I feel like Yoda watching Luke about to levitate the spacecraft. I'm so hopeful. Either do or don't do. Yoda was always saying those stupid things. Do or don't do. There is no try. What does that mean? Of course there's try. That's a quote from Buddha? Yeah. Yoda was quoting Buddha? Well, that sucks. I often thought that it would be, you know, easy to be Shakespeare because all you have to do is string together a whole bunch of memorable quotes. That's all he did, right? So, Mike, what's that little 5-pointed asterisk mean? You can't Google the 5-pointed asterisk because you don't know how to type it on the keyboard. And fortunately, all the work you're going to have to do occurs between your ears. Your fingers will not help you. The answer is right here in front of you. You have to use your brain, yes. It's correlation. That's what it means. So what this says is a correlation between f and g is defined as equal to the sum of the dot product, the sliding window dot product between f's complex conjugate, and g. That's what that says. In a fancy way. Have you ever heard of Guy Kawasaki? Yes? Rich is shaking his head. Who was Guy Kawasaki?
Motorcycle guy, and he also did a lot of stuff with tech.
Yes, yes, he did the tech garage. In fact, he's a venture capitalist, and also he's an entrepreneur. And I can tell you this, that he believes in the 10-20-30 rule, which is 10 slides in 20 minutes using 30-point font. Yeah, and he also used to be an Apple person. He was very big into Apple. So the reason why you need to have 20 minutes is because you usually have a 1-hour presentation, and you need the other 40 minutes to get the PowerPoint slides to work. Okay. Now, unless, of course, you have a Mac, and then it works fine. That's what he says.
What was that again? 10 slides, 20 minutes?
10, 20, 30. 10 slides, 20 minutes, 30-point font. He says if you're pitching to a 60-year-old venture capitalist, you need to use 30-point font. And if you, God bless you, are pitching to a 16-year-old venture capitalist, then go ahead. You can use an 8-point font. So yeah, that's the 10-20-30 rule. So here I'm trying to use that rule. So I've got basic points, right? And then if you start to read what's on your slide because you've cluttered it with lots of words, then people think you're a bozo who doesn't know their content. right? And then they say, I can read, I don't need you to read to me, and so everybody will read ahead and they'll stop paying attention. So cross-correlation is a sliding dot product. That's what it is. That's all it is. So fancy math, fancy notation, fancy name, simple idea. It's a dot product, and you take the whole thing and you shove it over by one increment, one sample, and then you do another dot product. And that's it. You're beeping. Stop the beeping. So then cross-correlation does the following. It measures similarity. It's template recognition. It'll take those fingerprints you've been looking for and allow you to see if you can find them. It'll let you find things like a head in a head and shoulders shot, or eyes, or a nose. You could build a nose detector. That might be good. Maybe you could find the tanks that are sitting around on the field. You'll get tanks of various orientation, and you could do your cross-correlation, and you could do what they call long-term photo interpretation, photo reconnaissance. So measuring the similarity between two things. Pattern recognition. Right? Pattern recognition says an image goes in and symbols come out. That's computer vision. So if I take a picture of all of the money that you put on the table and the answer is $1.25, that's the symbol, the symbolic representation of the money that's on the table. That's computer vision. So if you can take images in and make symbolic information out, you've made computer vision. If you want to do that kind of pattern recognition, maybe cross-correlation is a good way to do it. Maybe. Continuous cross-correlation doesn't use the sigma. Continuous cross-correlation is just like discrete cross-correlation with a difference. And the difference is it uses an integral. Otherwise, it's identical. It's the same thing. And guess what? The little 5-pointed star that we saw from before already is still there on the left-hand side of the equal sign. And that's a definition. So if we know these things, if we know the definition, then we have, I think, a relatively good chance of being able to do some proofs, interesting proofs, maybe easy proofs. And nothing I'm telling you, by the way, is anything that you couldn't find by Googling, probably. Like you could probably Google and cross-correlation, and they'd probably tell you the same thing. Maybe with different notation, I think. So autocorrelation, that's the same thing as cross-correlation, only with a difference. And the difference is, if you look back over in here, both f and g are identical. So what you want to do is you want to take the complex conjugate of f and then multiply it by the non-complex conjugate of itself, sliding, making a dot product of a function with itself. Okay, why would anybody want to do that? It's very popular in radar systems, very popular in real signal analysis, very popular for people who want to be able to do things with sensors that have noise. Sensors that have noise. Okay, let me ask you this. What sensors don't have noise? Can't think of any. Why? Because all sensors have noise. Unless you're living in the world of noise-free sensors, which is not my world, then you have to deal with noise. So what do you do when you have noise and you want to reduce it? Well, the answer is autocorrelation. If autocorrelation finds repeating patterns and emphasizes the repeating patterns, and the input is a repeating pattern, one thing that isn't going to be a repeating pattern is noise. By definition, noise is going to give us a random signal. So if autocorrelation finds and emphasizes those repeating patterns, what it will also do is remove the noise. That is key. That is so key. So autocorrelation, all of a sudden, that's sounding like a really useful thing, getting rid of noise. Because who doesn't want to get rid of noise? So if autocorrelation removes noise, I like autocorrelation. But I got a problem with autocorrelation. That sliding window dot product that runs in order n squared time is too slow. I don't want slow. I want fast. I want fast and I want no noise. So what do I do? That was actually not a rhetorical question. I'm going to start with a Rhodey again. Hey, Rhodey, what do I do? Uh-oh. I don't like autocorrelation. It's too slow. Brian, how do I make fast autocorrelation? Well, how do I do a fast convolution?
Convolution?
Yeah, suppose I wanted to do fast convolution.
What is convolution?
Uh-oh. You're killing me over here. We made a big deal about the convolution theorem, right? So correlation and convolution are just the same except for the lack of the complex conjugate. So what we wanted to do was try and I'm sorry you asked me that question, because that's a whole different question. What's convolution? Wow. Okay. Correlation can be done quickly in the frequency domain. The way you go to the frequency domain is with a fast Fourier transform. If you want to, just to answer your question, convolution in the time domain is equal to multiplication in the frequency domain because of the convolution theorem.
Okay.
Yeah, so you guys probably remember this, right? It's coming back to you now. I can't go back and start doing the convolution slides again because it's going to go crazy. It'll drive everyone nuts. But if you go back to the book and you look at chapter 5, you'll see that convolution is a big deal, and it's one of those things that justifies our study of the fast Fourier transform. Because if you can multiply in the frequency domain two functions and then take the inverse fast Fourier transform, you will have done a filtering. And that filtering is essentially what the convolution is doing in the time domain. It's just that it takes a longer time to do convolution than it does multiplication in the frequency domain, only because of the fast Fourier transform. So autocorrelation has more uses. Autocorrelation lets us do what's called fundamental frequency identification. So if you're trying to identify a fundamental frequency, this will help you do it. If you're trying to remove noise, this will help you do it. And you can do it fast in the frequency domain by going to a Fourier transform. And what this says is that fast cross-correlation can be obtained if you take the Fourier transform of a correlation between f and g. It will be the same thing as the Fourier transform of f times the Fourier transform of the complex conjugate of g. So I have an opportunity here to speed the cross correlation. If you took this fast Fourier transform multiplication in the frequency domain, if you wanted to get back to the correlation in the time domain, you would still need to do an inverse Fourier transform. In other words, we're in the frequency domain when you take f, take a Fourier transform, take g, take a Fourier transform, then multiply them. You're still in the frequency domain. The trouble is, you may not want to be in the frequency domain anymore. To get back, you gotta do an inverse fast Fourier transform. Gotta, or else you're still in the frequency domain, which is no good. So I have an opportunity now to do this in Java or whatever language you like, MATLAB, whatever, C on an Arduino, whatever you like. So if noise reduction is a way to justify the use of correlation, I can say that the correlation in time is equal to a multiplication by the complex conjugate in the frequency domain of a signal with itself. So take the signal, take its Fourier transform, make a copy of it with a complex conjugate, then multiply it by itself, then do the inverse Fourier transform, and voila, you have done a correlation that reduces noise. So when I look at this autocorrelation, it's in the continuous domain, the signal with itself, using the, how you say, integral, or if I like, I can do it in the discrete domain. And in fact, if you look at the two different forms of the expression, you will, I think, agree that they're practically identical. Does that seem right? Any questions about that? Autocorrelation is just like correlation, only with a difference. And the difference is F equals G. In this case, F equals G equals X, or whatever you want to call it. You done writing this down? Hurry up. Take your time.
Got it.
Okay. So here's the cool way to do an autocorrelation in the time domain. Take the inverse fast Fourier transform of the power spectral density, because the power spectral density is actually equal to the function. Take the Fourier transform and multiply it by itself. And what will happen there is you'll get a magnitude, then take the inverse fast Fourier transform of that magnitude, the absolute value of the magnitude, and voila, you've got an autocorrelation. Yes, sir?
Are you missing an absolute value sign, or is that extra? You see what I mean? I see 3.
You know what? This isn't right. There.
Okay.
How's that?
Yes.
Actually, if you think about the way we usually do this, is when we plot in a spectrogram, we use the power spectral density of the output of our Fourier transforms to get energy, to show power. And so what we're doing is we're looking at instantaneous power at every bucket in frequency. And the number of buckets in frequency is always equal to the number of samples which we have on input. So those frequency buckets can be traversing along a short window, if we like. And this would be called a short time Fourier transform based correlation, which you might call a short time correlation. A short time correlation might be really useful because you're reducing noise as your signal streams through your system. And if you can run your signal processing system in real time, which is the time it takes to keep up with the stream as it comes in, then in theory you do want a short time noise reducing correlation, which means a short time Fourier transform with the square term coming in and then the inverse term, so that you can proceed to reduce the amount of noise as it goes. What do you think of that? Eh? Good? Yes?
Just to clarify, the FFT, the absolute value of the FFT squared is the power spectral density?
Yes. PSD. So when it says here, the inverse Fourier transform of the power spectral density is the autocorrelation, what it's really telling us is, all you have to do is take an FFT of the signal, get the power spectral density, and then take the inverse Fourier transform, not of the original frequency domain version of the signal, but of the power spectral density of the signal. So you're using the PSD as input to the inverse Fourier transform. Yes, sir?
And then are we squaring it?
Yeah, what comes out is going to be squared. You may need to take the square root of all of it to get back to the original amplitude. So that's, I mean, yes, it comes out squared. Because what's happened is you took the signal and you multiplied it by itself, or its complex conjugate, before you took the Fourier transform. So by taking the Fourier transform, then taking the output and multiplying it by itself, you're giving you're increasing the amplitude. We can show that with a real example. In fact, we should do that. But so far, I think maybe what we've done is fairly doable in terms of subroutine invocations within Java. There's nothing here that we've done that's particularly aggressive computationally. Right? All we did was take a Fourier transform, I think, more or less. Save, don't save, save, save. Now what's up with this? The shape in any text cannot be edited when using earlier versions of PowerPoint. That just sounds like Microsoft came in here and piddled all over my prior versions of PowerPoint. And the moral of this story is never upgrade to anything that Microsoft gives you. And when it offers to upgrade, just say no. Just say no to upgrades. I guess I have to hit continue because cancel means I don't get to save anything. Because then now I'm incompatible. And the angels will weep for me because of my incompatibleness. That just feels really sucky. Doesn't that feel sucky? That's really sucky. What a sucky thing. Oh well, life in the big city. Too bad. Too bad on me. So now, what's this equalizer thing I've got? Is this your code, Rich?
Yeah, you changed
So this is spitting out all kinds of threads and things. I don't feel like this is your code anymore.
You didn't
didn't
open.
open.
You gotta open something. Yeah, you didn't open up audio data was empty. So when you change the sliders.
I was going to say you're inside of equalizer.java, but you are running my
Oh, I want to run equalizer. Thank you. Yeah, that'll do it. Can I play this tone? No. I really want it to play like a tone. I'm thinking there's another way to do this. Oh look, it's giving me all kinds of errors now too. Null pointer exceptions cause what? I didn't open up anything. Cause wonder if we should start from scratch. I think we should. Let's start from scratch. I don't like the idea of starting from something that we're not sure about. I've got this thing here, pink noise. Is that I don't want pink noise. I want regular noise. You know what I want? Let me tell you what I want and then I'll do it. I want a simple tone that I can visualize. Then I want to add noise to that tone. Then I want to do noise reduction. And I want to do the noise reduction with autocorrelation. That's what I want. Is that? Yes, sir.
How about the ECG data?
ECD.
ECG. You get a noise.
Oh, I could use ECG data. I know I could. And ECG data is a really very fine thing. And maybe we can do that later. But I'd like to start with a really simple tone. Because I'm thinking that it would be really swell to have a simple oscillator that gives me a really simple tone. And so I think maybe, I mean, there's a really simple tone here, but I can't hear it. Oh, I need like, yeah. That's a simple tone. I like the idea of simple. You know, a nice simple function generator. Now I had like an oscilloscope in here somewheres, Here's a dual trace oscilloscope, but I think there's just like an O-scope. And here's the O-scope panel. And I'm thinking that there's a little main method in here somewhere, so let me just find it. And here it is. And here's my main method, and what I'll do is I'll take the main method and I'll shove it to the bottom of this lovely little program. And so what am I doing here? I got 440 Hertz. I make 8,000 samples. I get a sine wave out of it, and I show it. And that's it. Let's see if that works. Yeah, good times. That's just what I wanted. Nice, simple sine wave. Okay? Everybody's good with that?
I'm sorry, what package are you in?
Right now I am in the sound package using the oscilloscope panel. And in the oscilloscope panel I found a simple program that lets me make an oscillator, get a sine wave, and show it. And I think what would be really swell is if I started a new class, because I want to do something interesting with, let me call it, I gotta give it a name. Java class. How about we call it auto correlation? That sounds like fun, right? Does that sound like a good name for a class? Auto correlation. And here's my little, oh, I need a main method in here. Public static void main, Control J, enter. Get rid of all this other cruft. Paste. And let's just run it and see it work. For good times. Yes. So what do you think of that? Nothing up my sleeves, nothing fancy, just an oscilloscope showing a sine wave. Now, suppose you want to take that 1 second of audio and you want to play it. Well, if you go to the U-Law codec, ULC equals new U-Law codec, and you put in the double data, you ought to be able to go to it and ask it to play the data, and you really ought to be able to hear it as well as see it, in theory. And that sounds like a sine wave. And if you go in here and you look at it, you can see there's 500 microseconds per division, 5, 10, 15, 20, that's not quite 25, so let's call it 20,000 microseconds. That's 2 times, what is that? I'll do it the other way. Let's do it in milliseconds. I think that's better. Then what we'll do is we can slide it until these things sort of line up. And now that's supposed to be 2 milliseconds. Yeah, that sounds right. 20,000 microseconds is 2 milliseconds? Okay, I'll believe that. So 2 milliseconds is how fast? I need like a calculator. Calculon. Okay, so it's 2,000 milliseconds is 1 divided by no, it was 2 milliseconds. 1 2,000th. I'm sorry. How many milliseconds is this?
It was 2 milliseconds.
2 milliseconds.
That was 2,000 microseconds.
Okay. So 1 over 2,000, right? Now if I invert this, what do I get? How do you want to do the inversion? Oh, 1 over x. So that says 2000 hertz. I don't know. I don't think we've computed the frequency correctly here. This is not supposed to be a 2 kilohertz tone, right? It's supposed to be 400 hertz. 400 hertz, 1 divided by 400 is now multiplied by 1,000, 2.5 milliseconds. So we should see a period of 2.5 milliseconds. So now, if we look at it this way, well, let's see. Having trouble. Oh, here it is. 1, 2, and that's supposed to be a half. So that's looking right. I backed it out the other way. Probably ought to build some sort of a proper frequency counter here. Oh, I know. That's what fast Fourier transforms are for. So anyways, if you go through the process of playing it and showing it, what would be involved in adding a little noise? Any ideas? Can I write a program for that?
Yeah. Can we use that?
For integer I equals 0 while I is less than dA dot length, I plus plus dA of I equals dA of I. Now, should it be additive noise or multiplicative noise? I think we're just additive noise, right? Plus math.random. Now that seems like math.random should be giving us a little guidance. It's a double value with a positive sign greater than or equal to 0 and less than 1. So that's a number that ranges from 0 to 1. DI goes from plus 1 to minus 1. So why don't we take this and subtract off a half so that there's no bias. And why don't we take the whole thing and multiply it by 0.1 so the magnitude of the noise is relatively small. So math.random goes from 0 to 1, but if I subtract off a half, it goes from minus 1/2 to plus 1/2. You follow me? So now if it's going from minus 1/2 to plus 1/2 and I multiply it by 0.1, it's going from minus 0.05 to plus 0.05. And then all I'm going to do is I'm going to take that noise and I'm going to add it to the original signal to make a new signal. So now I've got a sine wave with noise. And the reason I'm not using an EKG or anything like that is I want simple signals with simple noise. And this noise has a uniform probability distribution function, which is to say that it is not Gaussian noise, and it's not pink noise, and it's not fancy noise. It's just plain noise. And that sounded very noisy. It doesn't look very noisy. It looks just fine. But I can see that the peaks are not all quite matched up. And as a matter of fact, you can sort of see that there's something going on here. Now for a good time, if one has an idea of a good time, I suppose we could look at the fast Fourier transform of the signal prior to and after we've added in all of this lovely noise, right? So if one were to try and take an FFT and show it, what would you do? You guys now are experts, right?
Yeah.
How do you do that?
Let's call the class the FFT 1D double.
1D double, FFT equals new FFT 1D double. And does this take like arguments? No parameters. And so then, how does one take the fast Fourier transform here? FFT dot compute forward, and you put in the double thingy, and then you also need to have the imaginary part, double DAI, I'll call it, the imaginary part, which is also equal to a double, whose length is equal to DA dot length. And I guess you need a new thing in there, or else it's going to give you a hard time. And then you got to put in the semicolon because it's picky. And then you got to give it the imaginary array. And it's actually good that you only have to allocate that once, because you don't want to have to keep allocating these things, you know, inside of some for loop or something. So you do it once and it reuses the space, and that's very good. Yes, sir.
Quick question. How do we decide that the imaginary data is an empty array besides the
Oh, well,
That's
Java makes this default to 0. And you want your FFT to be the same size as your to have an imaginary array that's the same size as your real array. But now that we're talking about size, guess what? It's not an integral power of 2. But I can fix that, right? Because if you think about it, it's really 2. I can do that simply with a shift. I'll start with 1 and shift over, and 2 to the 2 to the 8. It's 8,192, which is going to be 2 to the 15, I think. Now there's somebody out there with a calculator who's checking me, right? Or I can just get a calculator and do it myself. 2 to the 15 equals, no, it's not right. So 2 to the 14 would be 16,000. 2 to the 13, is it? 2 to the 13 equals, yep, 8,192. So let's do this 13. So now let's see, what do we do here? We compute the fast Fourier transform. Does that give me a power spectral density? It does not. But I can get the power spectral density. FFT dot get PSD normalized. And that should return some kind of a double precision number. I'm getting buzzed here, excuse me. And now double PSD array equals, and now I think maybe we can go through and go to the O-scope panel and show the stuff. Show the stuff. What's the stuff? PSD. PSD. So what does that buy me? Well, that doesn't sound at all good. Maybe we should have made a copy, huh? Although it looks right. Oh, you know what? Ah, of course. The FFT destroys its data when it takes the Fourier transform, so we do need to make a copy. Let's see now. How shall we do that? How about double, let's call it DA for the FFT. I don't know what to call it. DA2? DA2 equals mat1.copy. Array copy. That sounds very efficient. Array copy, and you give it a double DA, and now what? Oh yeah, it's good. Now if you want to see how array copies work, I don't know if this one's any more efficient than anything else you have, but it's using a system invocation to the array copy system call. It's not a for loop, so it's supposed to be more efficient which is meaning, I think, that it's as efficient as any assembler language block copy that you can find with possible overhead. So that's supposed to be why you use mat1 array copy versus like a big for loop that just does a copy. I've optimized it. So now DA2 has got the data I want, so we'll use that for the FFT. And the rest for the noise, that should be DA1, that's noise. And we can show DA with noise. We've got the FFT without the noise. And I think maybe we're ready for this. So that worked. And here's the FFT with no noise. And I'd like to see the original signal. That's here, the original signal with noise. And now I'd like to see the signals DFT or FFT with noise. So I want to see it before and after with noise, before and after I've added the noise. So how about we do I guess we're going to have to do the following. We'll have to take an FFT again, only this time of the noisy signal. Now, the noisy signal which we're using on input, I guess we better play it first. Or we make a copy. I can keep making copies all day long, I don't care. Double DA3 array equals mat1 dot copy array and give it DA, that's the stuff with the noise in it, right? So now DA3 is used for the FFT. I'll need a new imaginary array, or I'll have to zero out the imaginary array that I've got. So I'll have to do some, let's do a new imaginary array. Double DA3I array equals new double DOU BLE, and I'll go DA3 dot length. And now what we'll do is we'll put in DA3I in here. So now we've got a Fourier transform of noise. So this will be the PSD of the noisy array. So now we're going to do something like this. Double DOU BLE PSD noise. That's the power spectral density of the original signal with noise. An array equals to FFT dot get PSD normalized. And now I can show the noise, which means I need another oscope frame because I want to see the PSD both before and after you've added noise. Think of how much more complicated this would be if I was doing this with an electrocardiogram. Right? All I'd used here was an oscillator. So let's recap. I was able to synthesize a pure tone. I was able to add noise to the pure tone. I was able to visualize and play the pure tone with noise. Then I took a fast Fourier transform of the pure tone and I showed you this power spectral density of the pure tone. Now I'm going to show you the power spectral density of the pure tone and the pure tone with noise. So you'll see before and after we've added noise. So here's the before, and that's very sweet and nice. And here's the after, and look how noisy it is. It's looking all noisy and crummy and crappy and everything. See? And noisy. See? icky, noisy versus nice and smooth. Eh? Eh? So it's now very clear. Now you have an opportunity to do noise reduction in the frequency domain. A couple ways you can do that. First, of course, is the autocorrelation, which we just discussed. What else could we do? Well, look how much amplitude there is in the power spectral density. Right? The signal has got a much higher amplitude than the noise. So you could develop a squelch control that goes in the frequency domain and looks for buckets below a certain threshold and just zeroes them out individually. You say, oh, that's too little. That must be noise. Zero it out. Go right on through, and then when you do your inverse Fourier transform, the only thing that'll be left is signal. That's good, right? I could do that. Right? How would that look? Well, suppose I said I happen to know something about the noise. It all has an amplitude of plus or minus 0.1. Or, yeah, I think that's what we did, right? 0.05. 0.05. So if I said anything below 0.0, let's say 9, or anything below 0.1 is obviously noise. Well, if I do that and I just put the kibosh on everything in the frequency domain, I'm good. I can do that. Right?
Yeah.
Why not? So let's go through, whoop, disconnect. So let's go through, I got this power spectral density thing. I can get all kinds of interesting information from that. mat1.getAverage. Get mean. Oh, get mean. So if I got the mean of this PSD noise, what would that buy me? Some kind of number, right? Presumably the noise is all below the mean, so let's just get that. Double, I'll call it AVG for average equals, and then at the end of the day I'll just print it. S out, Control J, Enter, A average, AVG equals, end quote, plus AVG, right? That's legit. I can do that, and I'm doing it in the power spectral densities domain. And maybe I'll call this average noise power. Poser. Uh-oh, my Freudian slip is showing. And then I can do the same thing with the noise-free power, right? Because I've added signal, so there must be more noise, but the noise might have neutral power. Oh no, it shouldn't have. It should have more noise. So average power can be something different. Let's call this average noise-free power, and we'll get the noise-free power by doing the same thing we did over in here, only with a difference, and we'll use the PSD, the original PSD. This is why I like to make so many copies, because I want to go back to those things. Get the noise-free power, and I want to see if the powers look any different. I'd like to see if they. I think they'll be different. I want to know. So let's have a looky-loo. We should see different power, right? So yes, the power with the noise signal in there, it's got a lot bigger on average. So if I use this average power and I say, look, any below average signal in terms of power, I'm going to put the kibosh on. That's a good time. I can do that, right? So suppose I did that in the I'm just going to get an arbitrary number here. I'll call it the average AVG, whatever that is, and I'll just go through my little I'll do my noise thing, okay? I'll say FFT dot is there any way to do noise in this? Is there any built-in noise filter? Squelch. Oh, that sounds like fun. So what does squelch do for me? Let's have a looky-loo. Squelch says get the PSD. Oh, it's using not normalized. I don't know how many people depend on it, so why don't we try a new one? We'll just make a new one called squelch for normalized. I think normalized makes more sense. So then it does a PSD normalized, goes through everything, takes the real data. If it's below the threshold, it turns it into zeros, and I think that's just fine. And so then what we'll do is we'll put in squelch normalized, and then we'll put in the average, AVG, and that doesn't return anything, I don't think. No, it does not. So then, now I can get the PSD from the FFT, normalized, and display it. And this will be a new array, and it's going to be called PSD squelch array equals. So now I've done the squelching, and what does that buy me? I got to show it, right? This has got to look different. Something happened. So let's look at the PSD squelch now that you've done all of this wonderful stuff. Will that work? Who knows? Let's find out. So this is supposed to be different from that. One of these two things is not the same as the other. Well, I gotta say, my squelch was, I guess I have to increase my squelch level. How about if we give it like a 6? Let's put a 6 in there. Because it did look a little different, but not as different as I would have liked. So,
when I showed the PSD after I put it through the squelch normalized, it came out smooth. Rather than recall, I like that you made an extra variable called PSD squelch.
you mean you put a number in here that was...
No. I put, since a squelch normalized changes the PSD, I just... Doesn't it?
No, it's using PSD normalized.
Oh,
It goes through and it changes these guys.
So we still have to get PSD normalized.
Yeah, when you call get PSD normalized, it should proceed. Oh wow, it calls not normalized, and then it normalizes it.
Okay.
So that's correct. I mean, I was using average. Maybe I should just increase it. How about if I use average plus a little bit? Let's go up to like 6. Now that looks quite different. Oh, I got rid of everything. I guess I was a little too aggressive. Let's try 5. See what happens. I was just I'm messing around. I don't know what the right numbers are. So it's looking like 5 was... Did I do something wrong with this average? Yes, sir.
It's with a negative 1 gram.
I beg your pardon?
Your averages are times 10 to the negative 4.
Oh, the averages are small?
Yeah.
Yeah.
Oh. Oh, hey, look at that. Averages are indeed very small.
With the median?
Well, I thought the average is, yeah, this is not good. That's very interesting. Averages are so small. Oh, I can see what the absolute numbers are. Let's take a look. So it's 0.0. This is millivolts, right? So it's 0.1. So I need numbers like 0.1. How about if I did 0.2? That might make more sense. Yeah, look how clean that is. Wow. That's slick, right? It was good that you spotted those exponents, because that was throwing me for a loop. So yeah, it turns out you now have the ultimate primo, cool-looking noise reducer using squelch. Now the question is, can you get back to your original signal without noise? And of course the answer is yes. You go through the process of getting your FFT and doing your inverse FFT, also known as a backward FFT. Or do I just call get inverse FFT?
Compute.
Oh, compute. Compute inverse FFT? No, it says backward.
Yeah.
But he's looking for the signal, the real and the imaginary signals, and presumably those were passed in when I did the FFT, and I lost track of which one was which. So let me just make sure I got it.
We can store the real and imaginary data whenever we do the FFT with the noise, right?
Say that again?
How about if we store the imaginary and the real data after we compute the FFT for the VSD noise?
Well, I thought it was also in there, but apparently this FFT, when it was computed, it seems like it should just use the internal. Yeah, I think there's more to it than this. I think there's something about getting the backward FFT that shouldn't require an argument, because it already has everything it needs internally. Doesn't it?
This is how I did my equalizer. I ended up having to store the real and the imaginary and re-putting it in the backward.
Well, can't you get the real? Yeah, here's the real data.
Yeah. Then I had to throw those into the backward the FFT.
Yeah, and here's the imaginary data.
Yeah.
So if you wanted to do FFT dot compute backward FFT, and this is wacky. I shouldn't need this. I guess I need a carriage return here. So now if you compute the backward FFT, then the real data should contain the original signal. Or let's see, I'll call it the filtered signal. So double filtered signal equals FFT dot get real data. Get real data. Okay. He's unhappy. Oh, you need arrays. Okay. Now I should be able to show the data. Give me back the real data. And that should be an oscope frame that's right on top. These oscope frames need titles. It's hard to keep track. So here we go. All very exciting. And here's the reconstructed data. Why is this so huge? Did I forget to normalize? I forgot to multiply by 1 over n. That's so important. So mat1 dot multiply the filtered signal by filtered signal dot length, but you got to 1f divided by filtered signal dot length, and does that give me an answer? Multiply, does it multiply? Yeah, it changes its argument. That should give me a normalized. Is this any better? Yes. And that looks like a signal.
One question.
Yes, sir. I gotta play it, but yeah.
Oh, 1f?
1 over f. Sorry, 1 over n. I'm multiplying by 1 over n to normalize the length of the signal. F, it means it's single precision float, because mult, oh, I guess I could have done it with a double. 1.0 if you prefer.
There's another
You can do it this way. D or F.
Oh, okay, I see. No, it's just there's another method, mat1 dot multiply, which takes 2 doubles.
Oh. Well, since 1 is an integer and length is an integer, I didn't want 1 divided by length to give me remainder 0. I wanted a floating point number. So to do floating point contagion, I put a floating point number in the numerator, and that would cause the division to become a floating point division. And so I was afraid that if I didn't do that, I would just be multiplying by 0, and then everything would be 0, because that's what happens. Because that's what happens when you multiply by 0, usually. So that was an extensive and long example for doing simple Fourier transform manipulation here. But now, I think maybe I can take the filtered signal, pump it into my U-Law codec, and play it. But before I do, I would like to do a thread.sleep of 2 seconds, because otherwise we'll have the two signals playing on top of one another, and that wouldn't be good. So let's see if we can play the original noisy signal, do our filtering, and then play it after we've removed the noise. Wait for it. Huh? 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 Good, right? And you know what that means? Break time. So what I'll do, I mean, that was a good one, because it actually worked. Thank God. And you know, it doesn't always work. It's nice to have a demo that works. So what I'm going to do now is I'm going to stop the recording, take a little break, and then we'll come back and we'll try an autocorrelation for noise reduction. Cool, right? Yeah, sweet. Alright, let's do that. And stop.